Hello, my name is Chris Schultz. I'm a water resources engineer and project manager with JO Consulting Group. Today I'll be talking through a technical assistance project that we performed in collaboration with Douglas County, Kansas, alongside the Kansas Department of Agriculture Division of Water Resources. This assessment was focused on hydraulic risk within the Wakarusa Corridor in Douglas County, specifically on the Wakarusa River between Clinton Lake Dam and the Kansas River. So first off, just wanted to walk through the agenda of the presentation. First, I'll be talking through context and some overall background of the project. Then I'll move into the approach and the overall methodology that was utilized. Next into findings and results, and then finally conclusions. So first off on project context. To provide some overall background on the project, I just wanted to provide a couple of snips looking at Lawrence over the past few decades. These are just snips from Google Earth showing what Lawrence looked like in 1985 versus 2025. And you can see just by the gray area, there's been fairly substantial urban expansion within Douglas County. And Lawrence is in a bit of a unique position in that it's bounded by a number of water bodies and floodplains, specifically the Kansas River to the north, the Wakarusa River to the south, the confluence between the two to the east, and then Clinton Lake, a large federal flood control reservoir to the southeast of the city. And as Lawrence has continued to grow, particularly towards the Wakarusa River Valley, this project, has the purpose of, trying to better understand hazard and risk areas, specifically high hazard and risk areas within that corridor area. So some initial background on how this fits into the overall process. There's an ongoing FEMA mapping process, which was performed concurrently to this by KDA and another consultant. This has been moving through the traditional process, beginning with discovery, moving into data development of the modeling and the mapping, and we'll move into preliminary flood map release and finally map adoption. This project again was performed concurrently to that, but utilized the draft two-dimensional rain-on mesh floodplain models, which were developed as part of that process. Really, this project had two main goals beyond that. One was to simulate a large number of flood events to understand varying risk scenarios, beyond what is traditionally looked at. And I'll get into that more in some of the future slides. And the second one was to really look at things in a different way, rather than just looking at the traditional outputs of depths and velocities, what we can get out of these models. Look at approaches to classify the hazard and understand where areas of high hazard within the corridor are. So next, wanting to dive a little bit more deeper into the complexities of flood risk. Kind of walking through the list here, the first and foremost is current and future development. A lot of the mapping generally looks at existing conditions. However, it's really important to understand, particularly in this area where the development push is really causing this project, what future development could look like and how that could affect both the quantity of the runoff that occurs, but also the timing, how development can change the ease in which water can move along the land surface, and therefore, the speed in which the water can aggregate and peak. There's a couple of components of precipitation which are also important. One is current versus future climate, understanding how precipitation could change within the future. Other pieces include precipitation intensity, whether, say, a 24-hour storm is evenly distributed over that time, or whether there's a large amount of precipitation during those specific times of those 24 hours. Also, the spatial and temporal variability in terms of precipitation, where that falls in the watershed, and whether there's a large amount of precipitation in certain areas and less in others. The Wakarusa River watershed also has Clinton Lake, a large flood control reservoir, as I mentioned earlier. So this has the effect of reducing flood risk through the Wakarusa River and upstream tributaries within the area. However, some consideration needs to be made for the coincident outflows from Clinton Lake alongside natural flows from the Wakarusa River. An example of this is shown in the plot on the right side of the screen. This shows the August of 2019 flood when there was a large release from Clinton Lake, during 2019, which coincided with another large natural flow event. Finally, soil moisture conditions are also important. Understanding how wet or dry the soil is can affect the amount of runoff that occurs. So next, moving into project approach. As I mentioned here, we leveraged a model which was developed by another consultant. So the first step of this process was to really try to understand, how representative this model was of reality. In order to do this, we developed a model simulation for the August 2019 flood event. To do this, we utilized best available data in order to develop what we felt like was a good representation of that storm, using MRMS precipitation data, gauge data from the Kansas River to represent backwater conditions, Clinton Lake outflows based upon observations, and compared soil moisture data to understand, what the antecedent conditions were, prior to the flood event. We developed this model and felt like it was a fairly good representation of, what was going on during the storm event, but then did some comparisons to better understand, how representative it was in terms of inundation areas and depths. In order to do this, we utilized photographs which provided by Douglas County, looking at where the inundation occurred during that event and comparing that to the model outputs. So here you can see a comparison from this photograph versus the inundation in the model output, with the star showing where this photo was taken. Generally, these comparisons matched up fairly well. Here, in both cases, we're seeing partial roadway inundation and full inundation further along in the photograph, and then you can see the roadway far in the distance. This is similar to what we're seeing within the model. Here again, this photograph is taken southwest of Lawrence. Here you can see the driver drove to the edge of the inundated area, and this matches very well in terms of where this inundation stops within the model output. So again, we're seeing a fairly good match between reality and what we're seeing within the model. Finally, in this photo, you can see there's inundation on both sides of where this photo was taken. Both to the north, there's higher depths and inundation where you can see the clear roadway in the distance, similar to the map. Alongside inundation also to the south. And if you look closely, you can also see the white line of the roadway showing that there's lower depth there to the south. And this again matches very well with what we are seeing in terms of the model outputs. Following the comparison of the August of 2019 flood event, we developed a number of different risk scenarios to better understand, a larger gamut of risk and hazard within the corridor, based upon the different uncertainties of flood risk that I talked about earlier. This included looking at a number of different storm events, the 10-year, 25-year, and 100-year storms primarily, with some other 500-year events included. Also looking at varying Clinton Lake outflows. Clinton Lake, within the Kansas City district, releases are determined by phases, phase 1, phase 2, and phase 3 within the flood control pool. These phases are determined by the stage of the reservoir and dictates the target flow or stages which occur downstream. So the higher the stage of the reservoir, the higher the phase, leads to higher downstream flows. Finally, we also looked at existing conditions versus a fully developed condition scenario, which includes development and elevated precipitation. So I wanted to dig into this fully developed condition scenario in a little bit more detail. The overall goal of this scenario was not to necessarily represent what's going to happen in the future, but to gain an understanding of the kind of risk uncertainty in terms of if this area was to be developed fully, how would that affect the overall runoff, which it can occur, which would occur, and also the timing in terms of the roughness of the land surface, and therefore understanding the risk which could occur to folks further downstream. So this had two major components. The first piece was looking at land cover. So this is a comparison very similar to what I was showing earlier in the presentation of the aerial imagery. This shows land cover from the National Land Cover Database comparing 1985 to 2023 in the western area of Lawrence. And the overall goal of this was to, leverage how growth has occurred within Lawrence in the past and utilize that pattern to represent what could happen in future development with the city of Lawrence. And the idea here was to, represent two major pieces that land cover affects in terms of the hydraulics and the amount of flows and inundation which can occur. One is infiltration versus runoff, and this is represented in the model as a curve number. So land cover can affect the amount of infiltration that can occur, increase the runoff, and therefore lead to higher peaks. The other important piece is the surface roughness, aka the ease in which water can flow along the surface. If the roughness decreases because there's a lot of concrete area, then that will make it so that water can flow more quickly and the peak can occur more quickly than in more natural conditions. So we looked at these areas in West Lawrence and organized them into several zones. Zone 1 being north of 6th Street, being primarily a commercial area. Zone 2 being more primarily residential south of 6th Street and kind of along K10. And then finally Zone 3 being south of Clinton Parkway and being more of a mixture of residential, but then also being adjacent to the floodplain with some significant undeveloped area. And in these three separate zones, we compared using that National Land Cover Database data, how the infiltration has changed, infiltration versus runoff via curve numbers changed alongside the Manning's roughness. And we were able to look at those changes and then apply those changes into other areas within the model. So in order to do this, we utilized Plan 2040 and the Comprehensive Plan Urban Growth Boundary, specifically tier areas 2 and 3 in terms of where growth is anticipated within the near future. We applied those changes in land cover via infiltration and roughness to those tier 2 and tier 3 areas to try to represent how those changes would occur if development were to occur within those areas. The final piece of this scenario was precipitation uncertainty. So this table shows a comparison of the 24-hour precipitation using the NOAA Atlas 14 base estimate, which is used in the existing conditions model run, the upper 90% confidence interval of that NOAA Atlas 14, which represents NOAA's uncertainty in terms of the upper bounds of what that 24-hour precipitation could be, as well as climate-based precipitation data used in a past study. Ultimately, here we utilized the upper 90% confidence interval because it exceeded the precipitation value and really allowed for potential future resiliency in terms of taking into account some of those other variables of precipitation uncertainty I mentioned earlier. So next year I'll move into project findings and talk through our approach in terms of developing the hazard and risk classification for areas within the corridor. So overall, the goal was to move beyond some of those traditional model outputs, the depth, velocity, depth times velocity, and move into something that's a little bit more valuable and tangible in terms of understanding areas of high hazard. If development were to occur in these places, how would the people be affected by these flood events, homes and businesses, and vehicles driving through? There are several different approaches to do this. Fundamentally, they're fairly similar. Using the model outputs, depth times or depth velocity, etc., and these hazard vulnerability curves, we can then set about and classify based upon depth and velocity thresholds, different hazard classifications, uh, within the simulated model area. There's several different approaches to do this. There's an Australian approach, which is very well documented and works very well in terms of breaking down the hazards and the different thresholds for people, structures, and vehicles. There's a FEMA approach, which I'll dig into more through the remainder of this presentation. And then finally, a Bureau reclamation approach, which is more focused on dam breach inundation and is aged quite a bit at this point. For this project, we utilized the FEMA flood hazard classifications. These classifications are separated into 5 classes: low, medium, high, very high, and extreme. On the figure on the right, you can see those classifications thresholds. These classifications use thresholds based on both depths and velocities, but then along the curvature of the line, you can see depth times velocity then becomes important as well. And these thresholds then serve as the basis of classifying flood maps. Using direct model outputs, then you can separate and better understand areas of higher and lower class hazard. This is an example based upon our model outputs, looking at the 100-year storm, Clinton Lake Phase 1 releases under fully developed conditions. And you can see, after we apply those thresholds to the model output, it really helps pop out areas of those high, very high, and extreme hazard classifications. While there's wider spread inundation that occurs, you can see some of those areas where the hazards are elevated. And I'll dig into why certain areas have higher hazards here on later slides. So the next step in our process was to then dive into more detail in terms of the different scenarios. So this again shows the 100-year storm. In the background gray, you can see the overall extent of the existing conditions scenario inundation. But in the foreground in blue, you can see those areas of higher hazard under existing conditions. And then in darker blue, you can see that expansion, based upon that fully developed condition scenario, which includes both the development as well as that higher precipitation. The same base map annotated with some of the key areas in terms of where high hazard areas are occurring, within the river valley. Moving from west to east, you can see, just below Clinton Lake Dam, the high hazard areas are really diminished alongside the flood risk due to the storage of the Wakarusa River and upstream tributary flows within Clinton Lake. Some of the higher hazard areas begin to occur as the tributaries flow in. Yankee Tank Creek as well as Washington Creek begin to flow in just to the east. And you can see, specifically to the south, some of the Washington Creek flows enter the Wakarusa River. However, some also flow along this overflow path to the south and through a different route under US 59. Additionally, there to the north, there's another overflow path moving further east. Another key piece of this in several areas is the importance of the terrain in terms of understanding these areas of higher hazard. Specifically, you can note that there's lower hazard, which is being shown directly adjacent to the Wakarusa River south of Lawrence. What we found looking at the terrain is there's actually areas of elevated terrain within this area, and that is diminishing the depth and therefore the hazard directly along the Wakarusa River. The effects of the terrain are also shown further to the east, where you can see the effect of an old Kansas River meander in terms of increasing the depth and increasing that hazard area or the hazard within that area. Finally, moving to the east, some of the overflow paths converge and that area of high ground along the Wakarusa River reduces and you see more of a traditional floodplain inundation in and around the Wakarusa River. Similar maps were developed for other storm events. This shows the 25-year storm. Similarly with gray showing the overall inundation extent of the existing conditions, the lighter orange showing the existing conditions, high hazard areas, and then the darker orange showing those areas added with development. So this 25-year storm occurs more frequently than the 100-year storm. Overall, the inundation patterns here are similar. While the inundation extents are reduced, the key features which cause them, the overflow paths and the high terrain, remain persistent. Similarly here, in the 10-year storm, this would be the most frequent event. Once again, the patterns in terms of what's causing the inundation are similar here in terms of those overflow paths, and then the inundation directly adjacent to the river further to the east. Finally, moving into project conclusions, just wanted to highlight a couple of the main key pieces of the project. First of all, some of what we're seeing here is the importance of evaluating a number of these different risk scenarios. Specifically, not just looking at how things are right now, but better understanding what could occur into the future, both in terms of potential future development, as well as changes in precipitation. Another key piece here is the understanding of the terrain features and how they dictate the flow patterns and risk. As I highlighted in the previous slides, the terrain dictates the amount of depth and therefore has a large influence in terms of where these hazard areas are shown. So with that, I thank you for your time.